Okay, my members from the Byte family, welcome to this lesson 4 of our chapter Logic Gate. Today we are dealing with the universality of the NAND and the NOR gate. Remember in lesson 1 when we were discussing the different types of logic gate, we found out that there was a category of logic gate known as the universal logic gate, and we defined them as logic gate which can be used to derive any other Boolean function. Today, we have to look at how these different universal gates can be used to derive the basic logic gate. Can you list me these different basic logic gates? Correct. We have the AND, the OR, and the NOT gate. Okay. Now, the NAND and NOR gates are called universal gates since they can be used to derive any logic expression. Below will be demonstrated how these universal gates are used to implement the AND, the OR, and the NOT gate. Universality of the NAND gate. Okay. Now, how can we use the NAND gate to derive the NOT gate? First of all, when we have an input A, we pass it to the NOT gate, it gives us A bar. Good. Now, we know that now we have to express the NOT gate in terms of the NAND gate. Okay. Since the NOT of A gives me A bar, and A bar is the same thing as A dot A all bar, remember that the NAND gate takes in two inputs and gives what? The dot, the complement of the dot. So since you have A dot A all bar, it's just as if I have A NAND A, meaning that what? The NOT gate is similar to having a NAND gate with only A as the input. And here we are using what? The junction. So this is what we are having. This is my NAND gate. Remember that if it was A and B, I will have A dot B bar. But since it is A and A, I have A dot A all bar. And since the A dot A gives me A. So this is how the NAND gate is being used to derive the NOT gate. Take note that in the exam, if you are being asked to express the NOT gate in terms of the NAND gate, it is very excellent and it shows that you master the concept. It will be very good for you to demonstrate as I did here first of all before you draw the gate. Okay, let's proceed. The AND gate. We know that the AND gate, the AND of A and B gives us what? A dot B. And now we need to express A dot B in terms of the NAND gate. Okay. A dot B gives me what? A and B gives me A dot B. And now I use the counter double complement because A dot B is same as A dot B with a double bar. Okay. Now, being with a double bar now, A dot B with a simple bar can still be written as this times it because these two. Remember that any input times itself gives me back the original input. So this times this will give me A dot B bar. With this bar now gives us the double bar. And A dot B with the double bar gives me AB. So this is how I derive the AND gate in terms of the NAND gate. Now as you can see, this is A NAND B. This part, this is A NAND B. And now it is being multiplied again by himself. That is why at this level, I have a junction to show that this is A dot B and this is A dot B. A dot B bar, this is it, times A dot B bar. These are the two. Now the NAND of it again, that is why I have another NAND gate which produce AB because this times this brings me here and this brings me here, which is the AND gate. The OR gate. A or B gives us what? A plus B. So we need to know how to express A plus B in terms of the NAND gate. We know that A plus B, I use counter example on each of them. So I have A double bar plus B double bar. And now I simply apply De Morgan's theorem. That is A, I consider this to be X bar plus Y bar will be what? Y, X dot Y all bar. So I consider A bar to be X, I consider B bar to be Y. So this will give me X bar plus Y bar. And from De Morgan's theorem, X bar plus Y bar gives me XY all bar. Now, A bar dot B bar, other bar is the NAND gate. So A bar, NAND, B bar. How can I obtain A bar now using the NAND gate? Using this concept. How can I obtain B bar using NAND gate? Using this concept. So I'm supposed to have this for A, then this again for B, Then at the end, you simply use a NAND gate to combine them, as you are seeing here below. A bar, B bar, then it gives me A or B. Universality of the NOR gate. We start with the NOT gate. With the NOT gate, it is the same concept. Instead of dot, we simply use the plus. As you can see, A is equal to A bar. A is the same thing as A plus A. And A plus A all bar is the same thing as A, NOR A. And that is what we have. That is how we express the NOT gate in terms of the NOR gate. Now, for the AND gate, we know that A and B is A dot B. A little secret that I'm going to tell you. Expression of the NOT gate in terms of NAND and NOR is the same, as you can see. But expression of the AND in terms of NAND is the same thing as OR in terms of NOR, and OR in terms of NAND is the same thing as AND in terms of NOR, as you can see. Look at A plus B, A dot B, double complement, double complement. Then I simply add them, as you can see. So I'm going to have this for A, this for B, then with a simple NOR gate, as you are seeing, so that these concepts are similar. So that is how it is. Double complement, you apply the Morgan theorem and everything is okay. Or again, as you see, you could realize that this and this are almost the same concept because this is A nor B, then NOR of their result. As simple as that. So guys, this is how the NAND and the NOR gate can be used to derive the basic logic gate. At the end of the chapter, we shall come across GC question where we shall also see some question where a different expression is given and we are being asked to represent the gate in terms of a universal logic gate. So for this lesson, it was all for today. I hope you guys understood the concept. In case of any question, send it in the comment section below and don't forget to like, subscribe and share. Okay guys, see you for the next lesson where we shall be introducing the sum of product and the product of sum. Thank you very much. See you next the next class. My bye team.